Hello everyone. I'm Pixi from Tsinghua University, and the other author is my supervisor Li Xiangyu. I'm honored to have the chance to present to you our latest work on the lightweight online semi-supervised learning algorithm for ultrasonic gesture recognition. Here is the outline of my presentation. So hand gestures are one of the most natural forms for nonverbal communication for humans, and is considered an efficient method for human-computer interaction, or HCI. As shown in Fig 1, various sensors, including cameras, wearable map sensors, and radar sensors, can be deployed in the front end of a practical gesture recognition system. Among all these choices, radar-based system has several important advantages, including its contactless interaction mode, its independence of light condition, and its smaller probability of privacy leakage. So they have made the radar-based gesture recognition one of the most competitive choices. And Figure 2 shows the famous millimeter wave radar system SOLI, which is developed by Google. And compared to the radio frequency radars adopted by SOLI, acoustic radars produce signals in much lower frequency and have the potential to further cut down power consumption. And so we have focused on the ultrasonic-based recognition for embedded applications. And Fig 3 shows the process pipeline of an ultrasonic gesture recognition, or UGR system developed by Avalab. So robustness is one of the key challenges of the gesture classification algorithms. Machine learning methods, including k-nearest neighbors, support vector machine, convolutional neural networks, and long short-term memory, has been commonly used for gesture classification in previous studies, which basically belong to the category of offline supervised algorithms, where pre-collected data set is required. However, due to the high spatial temporal variability of the gestures performed by different individuals, for example, a example is given in Fig 4, pre-collected samples from training participants usually fail to finally approximate the gesture distribution of the final product user, and leading to relatively worse model generalization ability on users. So to enlarge the data set by hiring more participants may be a solution, but it is often too expensive to execute. So a possible solution is to make use of the gesture samples incrementally captured during the life cycle of the product by employing an online semi-supervised learning algorithm. The reason behind is the hypothesis that the gesture characteristics of a specific user are unique and stable. Thus, those incrementally captured gestures sampled from the varied distribution of the actual user are the best training materials. And additionally, those samples are potentially huge in quantity. So to utilize those sequentially arrived unlabeled samples, the training algorithm for an embedded UGR system should be capable of modifying the model parameters or structure due to the incrementally arrived samples, but without a massive storage of the captured samples. And it should also be capable of extracting necessary information from the unlabeled samples. However, we found that the few studies have investigated the non-offline supervised algorithm in the radar-based gesture recognition. So it motivates us to build a prototype. So before going to the algorithm design, firstly, I'd like to briefly introduce our system setup. As shown in Fig 6, one transmitter and spread receivers with 40 kHz ultrasonic transducers are employed in the front end. We are coherent path string with 1.5 microseconds PRI and 0.1 microseconds pulse width is emitted, and 3 channels of echo signals are received. FPGA board is used for stimuli signal generation and basic signal processing. Then the digitized echo signals are sent to Pixi for further signal processing, namely IQ demodulation, downsampling, range Doppler map generation, feature extraction, and finally the classification or the proposed incremental training. Now I'd like to introduce the algorithm design. The architecture of the proposed classifier is shown in Fig 7. The extreme random forest, or ERF, is adopted as the basic building block of the whole classifier for its gesture classification performance parameter, while its training complexity is relatively lower than the random forest. The one versus rest strategy is adopted. And for each gesture class, there is a binary ERF, which comprises two subforests, which I call referential subforest and incremental subforest, both of which are of size 50, and the maximum depth is said to be 4. Forest gave probability that a sample belongs to the corresponding class, and the gestures are finally claimed belonging to the class with the highest probability. The referential subforests are trained in the offline manner by the traditional ERF algorithm, while the incremental subforests are trained online using the newly arrived unlabeled samples. So the overview of the training flow of the Hive incremental subforest is shown in Figure 8, which could be divided into 3 phases. Each time a new sample arrives, firstly in phase 1, a pseudo-label denoted by LPGS and probability PRGS are given by the ICE referential subforest. Then in the phase 2, samples with probabilities lower than the threshold will be discarded. Finally, in phase 3, samples past the filtration will be used to incrementally split the leaf nodes of the referential subforest with the proposed module of feature catch and index pools, which I'll introduce later. So we use the referential subforest as a pseudo-label predictor, but it actually suffers from worse generalization ability on the non-participant user samples. So the misclassified rate of pseudo-labels is non-negligible. And we have found the confidence distribution of the misclassified pseudo-labels is relatively lower. So a threshold is set to filter out those low confidence samples. Empirically, we would choose the value that best balances the resampled pseudo-positives and negatives at the threshold. So to limit the space-time complexity, we propose two modules, namely feature catch and index pool, to realize the centralized access for pseudo-label samples. And as shown in Fig 10, each time a new sample GIs arrives together with the index IDGS and pseudo-label LPGS, instead of distributing their massive amount of copies to all of the deletion leaves, they will be deposited as a whole into the feature catch, which is the low capacity buffer, while only the indices are stored in the index pools, which are maintained in the leaf node and the incremental subforest. When the gain index of a specific leaf exceeds this threshold, samples are fetched from the feature catch according to indices stored in the index pool and used for incremental splitting of that leaf node. Now comes to the experiment and results. And as shown in Fig 11, totally 8 gestures are defined, including the swiping, drawing back, pushing, splitting fingers, pinching, beckoning, and finger sliding. And totally 7 volunteers participated in the data collection, whose names are abbreviated here using their names' initial letters. And totally 100 samples per class per participant were collected. So we have 800 samples per user or 700 samples per gesture. And to simulate the actual scenario where user samples are not pre-accessible, 7-fold cross-validation is used to test the model, where each round 1 participant is specified as a user. The non-user samples are used for pre-training for the referential subforest, while for the user samples, half of them are used for incremental training of the incremental subforest, while the remaining half is left for testing. This page shows the recognition accuracy achieved by every model in any aspect of gesture. And the accuracy of each gesture is achieved, is averaged over the 7 users. A maximum improvement of 10.8 of incremental subforest against the referential subforest is achieved on the 6th gesture, G6, and a minimum improvement of minus 0.3% is achieved on G2. And the average accuracy improvement is 6.3%. And when we view the recognition accuracy in aspect of user, a maximum improvement of 10.7 of the incremental subforest against the referential subforest is achieved on the user ZXM, and a minimum improvement of 3.1% on GG, which shows that the by the incremental training, the user experience could improve. And thanks to the feature catch and sample pool we introduced are limited in capacity, sample missing when splitting a node may become a potential negative contributor to the model performance. And according to the experiments results shown in Fig 13 and 14, the capacity of feature cache and index pool could be set as low as 80 and 20, respectively, without introducing significant performance degradation, which means the maximum amount of pseudo-labeled samples to be stored over the whole process of incremental training, and the maximum amount of samples to be processed in a single splitting of a link knot could be controlled within 80 and 20, respectively. This gives the algorithm the potential to be employed in the resource-restricted embedded systems. So to conclude, an URF-based online semi-supervised learning algorithm is proposed for ultrasonic gesture recognition, and to limit space-time complexity, feature cache and index pools are introduced. And finally, experiments show that the proposed algorithm could effectively utilize the real-time collected and labeled samples to improve the personalized recognition performance. And this is my reference. And thank you. If you have any questions, I'm happy to answer it. Thank you very much.